My name is Taniel Põld, and I'm here to speak on this ambiguous topic of microservices and monolith. First of all, I have to make a disclaimer because I accidentally placed this talk in the hardcore coding track, and although it might be a bit more towards the cloud track, or it's in between, so you will not see examples of how you can optimize just-in-time compilers in Java virtual machine in this talk. But hopefully it will be interesting for you. So about me, I work as a software architect at a company called Playtech. I worked in IT industry for past 7 years. Last 5 years I've worked on concurrent and distributed systems in Java, and on my free time I play Dungeons and Dragons. About the talk, I will give an overview of the challenges that we've faced in Playtech with our monolithic application structure. I will talk about a project that we had last year, where we tried to break it down. This is a continuous process, so we're in the middle of it. I will talk about the plans that we have for the future and the challenges that we've encountered with moving towards the microservices architecture. Shortly about Playtech company. It is a company that produces gaming software. We have 23 large offices around the world, more than 3,700 employees, 480 employees in Topconf, which you can see on this image. If our office would have been in Second Life, if it would look like something like this, but in reality it's not 3D rendered. We have an office in Tallinn, which has 140 people, and I am from the Tartu office. But we're not dealing with only dealing with the gaming. For example, I come from the department called IMS, which stands for Information Management System, and it basically deals with everything which is not related with gaming. So it is CRM, players' wallet sessions, authentications. We have our own support chat solution. There are regulations in different countries for which we have to follow in order to work on these markets. So there's a lot of things going on, and I haven't seen the games we are making, or I haven't touched them for over a few years, and so I'm not really aware of what we are really making or what the other parts of the company is making. This IMS department, it has approximately 100 people. We have 20 different deployable servers, and there are 9,000 server instances of these servers that we have to support across all sites. There are approximately 50 sites which we are running on our own server park, and we are using VMware as a virtualization layer in there. And the code base in IMS department has evolved approximately from the year 2006. There's probably some code which really originates from the 2001 even, maybe, but most of it comes from the 2006. So it's evolved over the last 8 years. So I will come to the challenges that we've had with our monolithic application structure. These are the challenges that we have in general. Our applications are using a central Oracle database. So this is a bottleneck in our application stack or monolithic application stack. In some of the sites, there's a really huge transaction volume. For example, 320,000 transactions per minute is made in some of the sites. And the database does not scale horizontally, but it scales vertically. So that if we want to create bigger sites, we have to buy better hardware, and the Oracle licenses cost a lot in this case. Then, of course, we have high availability requirements, because a lot of the licensees to whom we are providing this software, we're renting it out to our clients. They are really agile in moving between different software vendors. So if you would have long downtimes, or they don't even have to be that long to upset our licensees so that they would move with their business to another vendor. There's the data integrity requirements, because we're dealing with monetary data, and we have to report it to the regulations, to the licensees, to the governments, tax offices, and we are also having problems with the virtual machine license costs, because VMware is billing us per VM cost, and we have a lot of those, because at the moment we are usually deploying our application in separate VMs. So then in total we have a lot of VMs, and the costs are accumulating. And then we have problems with up and down scaling, because if, for example, we have a site, and we are seeing that it has a lot of load on it, and we somehow have to deal with it, then of course we can go and add some new virtual machines, and we have a special backend for it, for adding new virtual machines, adding new applications in there, scaling the site up. But it is still somebody is doing it manually. Somebody has to go into this backend interface and click those buttons, and eventually we also have sites which are shrinking, so that they don't have as much load as they did before, and now somebody will have to go at some point and remove these virtual machines. This is actually a more difficult problem, because usually if you're setting them up, then you have a priority, but taking them down, it's like you have to decide that, okay, now I will remove them. And we have in recent years we've had problems like these, which are really high peaks in our system load. This, for example, is a few years ago in the event called Grand National in UK. So it is a horse racing event. They really like to watch how horses jump over hedges. And the blue line, which has this high peak, is the number of logins per 10 minutes in this case, because it's a few years ago, so it's the load is not that high, but the blue line is sports betting site, and then the other lines are bingo, poker, and casino sites, which are not the same site, but they are having quite high loads. And so, as you can see, suddenly we get from a sports betting site a huge number of login flows. Flows for which we are not prepared for, because usually we get gaming, and this is what we want to deal with, and then normally our other sites they get the users the user logins are really in small numbers at the time. But in this case, within one day we get a really high peak, a lot of logins, and the login flow in our case is not optimized, and it wasn't optimized, and then. Yeah, it was like came a bit as a surprise. So these are the challenges, and now we've thought about them, and we've looked into the direction of microservices as a solution. Because okay, so how many of you know the microservices software architecture paradigm? Or could you raise your hands? Okay, I will come to it. But basically, it promotes high availability through failure, and in this case, and it also promotes having data stores per service, and auto-scaling solutions, and open source software, which kind of would solve some of our problems, and hopefully most of them. So I will give us short overview of what the microservices architecture is about. A really short few slides. So in microservices, the idea is that you will deploy every service as a separate server. Each of these services have their own repository. They can be developed by different small teams. These small teams will not collide when committing into this repository. They can be written in different languages if you desire so, and each of these microservices is focusing on one business aspect or capability. They are communicating over asynchronous APIs, because in the service-oriented architecture you usually separate the services with the interfaces, and then you have this synchronous Java interfaces, so you call a method and it gets executed in another service inside of the same application. But in microservices you have these asynchronous APIs that you can use over a network. They have decentralized data management, which means that each of these services owns its own data store, and you can and all data is accessed through this service, and so you can replace the data store behind it. In case of failure, only a small part of the system is affected. So if you manage to code some sort of a nasty defect in your system, in case of a monolithic application, you probably feel it over all aspects of your system. But in case of microservices, you hopefully only affect a small part of it. And you can deploy these microservices separately per need. So for example, in this diagram, if you would need 4 services dealing with gaming and only a few for authentication and payments, then in microservices you can deploy 4 gaming services and 1 for authentication and payment service. But in case of monolithic application, you would have to deploy this monolith probably 4 times, so that it would deal with a gaming service, and then the authentication service part in it would not get as much load. So this is a short overview. In general, it is a much larger topic, and there's a lot more about it. And now we reach to the main part of this presentation of how we try to move towards this microservices approach. So over the last year we had a larger refactoring project in our department, and it is still ongoing, because if you take a large legacy application, there's a lot you have to do, and within 1 year there's only a limited things that you will be able to do. But what we started with was our server called Nova, which is a really dull name, especially taking into consideration that OpenStack has a server called Nova in their system. We actually had a voting for picking the name, and the second closest was Death Viper, if I remember correctly, but unfortunately it didn't win for the server name. But so it is a standard Java server. The services are defined in the API level. It had vague service boundaries, so we had a few of the classes which we knew belonged to one service. We had some of the classes which we knew belonged to the other one, and we had a lot of gray area in between. And it was and it still is developed by 2 teams, approximately 14 people. So we started with splitting this application into smaller parts, and especially into smaller modules. So first of all, we mapped the services which we wanted to achieve out of it, and then we started creating a huge number, for us at least it was a huge number of modules and different repositories for these. So each of the services would get one API module and one implementation module, maybe modules in this case, and altogether we got them approximately 10 or so from this one application. And the idea was that this API module would contain Java interfaces for data types and operations, so that the other services would have a dependency on this API, and they would not have to know about the other services implementation. And eventually we moved our protocol, service protocol definitions into these API modules as well. And all of these services were still and still are deployed together as one application. So what we got was this kind of tiers, which maybe illustrates the idea a bit better. The dependencies in these tiers can only be vertically, not horizontally, because if you have horizontal dependencies, let's say that the one API module is depending on another API module, you end up with dependency loops, or you may end up with dependency loops. So in order to not get those loops, we had tiers. So up there is the common or core modules. Actually, there are more of them, but those are common for all the services inside of this application. So in the middle we have this a few examples of the API modules, and down there we have the implementations. And the implementations have dependencies on the API modules which they require, and on the common module. And when we did that, what we ended up with was a lot of API modules which contained a huge number of Java interfaces. Because at first, if you split these services from one application, you still have these synchronous Java interfaces and method calls, and you just want to get these services separated. And so we had these APIs which contained a lot of interfaces, and so if one service would call the other service's API, the Spring would found the correct implementation for it from the implementation module, and would do its work in there. And we also had a solution for asynchronous calls, because we were using them in our monolithic application as well. So these were a proper. They were using our internal protocol called Galaxy, which is a binary protocol, so they are all executed with asynchronous logic, so that you send a request into a central router, and it is routed into a correct service, and it gets solved in there, and later on you get a response. And meanwhile, while you are calling it, the thread will take another piece of business logic that it will work on, and it will not be blocked. But so to clean up these service API modules, we created an adapter that would allow for this legacy code from in this case the service A, or from one service, to call synchronously the asynchronous code which is in another service. So that the use case for this was that, let's say that we have one service with a developer who is really knows about the code in it and how it works, and he's starting to refactor it. But this service gets a lot of synchronous calls from the other services, which this particular developer has not that much knowledge about. And so, to replace this synchronous call with an asynchronous call, the developer would have to deal with the code simultaneously in both of these services. But in order to solve this without this need, we created an adapter which allows to call the code synchronously, so that the developer who is working in this case with the service B is creating a asynchronous logic for the previous interface realization in this diagram, and then he goes into the service A and he only switches this call with a call to the adapter, so it's still a method call, and it's a really easy switch to make. And the service A works, it still works, but of course it needs refactoring later on. But this developer can then remove this Java interface class from this service B API in this diagram. So this is one of the methods that we used, which may be useful, which maybe work in some other cases as well. And another thing that we did was the data decentralization. This Nova server, how it worked was initially it had a central data access layer. It was used by all of the application logic all over the place. So all the services went into this, used the same data access layer. They used the tables which they needed. And what we wanted to do was we wanted to separate this or decentralize this data management, and to reach into a solution where the data is owned by the service itself, so that everybody who wants to alter this data or access this data would have to go through the service which owns it. And so we started creating the schemas, separate schemas in our Oracle database for different services, and these services would own the data inside of these schemas. And well, the purpose for us in it is that in the future we hope that we can move this, for example, in this diagram, the login services data into another data store, so that because the login services data integrity requirements are different from the wallet service. For example, because in the wallet service we are dealing with monetary transactions, and it is easy to use Oracle with its ACID properties and guarantee that everything reaches the database simultaneously, and all the data is in there. While in the login service or in the authentication domain, we don't have this kind of requirements, because if let's say that at one of the sessions gets lost in some point of time, and then what happens is that the player will probably have to either log in again, or he gets some sort of a glitch in the system, but it is nothing critical. He can come back or try it again, and we lose the data about this session, but it is not critical because we don't have to report it to some licensees or regulations. So this is the purpose why we're moving in this direction. And with this 1 year of refactoring, where we got ourselves was we have the services in separate modules and in separate repositories. The inter-service or inter-application communication is done over APIs. Most of them are in asynchronous, but there are still some Java interfaces and method calls in there which need to be removed. We tied the application together with the Spring injection magic, and we are in the middle of decentralizing our database to move the load off from the Oracle, which is our bottleneck at the moment. So about our plans for the future. We've made a small proof of concept to pick a direction, and we are evaluating with this proof of concept. We were evaluating the Cloud Foundry as a middleware in our system. Why Cloud Foundry? It's because it has the idea of these containers which you can initiate almost immediately. They're called DEAs. I can't recall what this acronym stood for because it was really unintuitive. But these containers in Cloud Foundry, you can start them up within I'm not sure what was it, milliseconds or really within seconds. And if you compare it to a virtual machine, if you create a new virtual machine, it comes up in it takes ages compared to this. And the plans with the Cloud Foundry is that with these containers, which are kind of like JVMs, we can create applications which we can place our future microservices inside of these containers, and we can create a solution where these microservices would be automatically created, and site would scale automatically. But coming back to this proof of concept, in this diagram, you can see this Nova server, famous Nova server, which is still communicating with the Oracle database, and this existing router is one is the solution for routing between all of our servers. So we created a simple proof of concept with a RabbitMQ and one new service which used ACL libraries and Cassandra just to see and then test this direction. And so this is something which we want to explore more in the future. We also want to create data stores based on service needs, move this load away from the Oracle. And as I mentioned, we want to get auto-scaling microservices. Now the challenges that we've had with this approach are moving in this direction. First of all, there are some in a monolithic application, or at least in ours, we had some occasions where we had a database transaction which was overlapping multiple services, so that it was used to roll back the data from this transaction if something went wrong, and then it was used over multiple services, and so we had to somehow redesign these business flows. And fortunately, it was possible, but because the alternatives would be to use some two-phase commits and some more complex solutions. So it was something which took us a lot of work to redesign these business flows. Then we got a decoupled system overhead, because for example, this Spring, which we started to use more and more, in some of our performance tests we saw that it created even up to 10% of CPU overhead in the login flows, mainly because we were abusing the Spring, because we were creating objects on every request which came in, and we were not reusing these objects because of the legacy solution that we had before. Of course, there's more communication. You can't just call a method in another service, but you get get a lot of calls moving around inside of this this monolithic application. And if you would move it into the network or separate these services, this overhead will definitely increase. So we also have had some flows that passed through multiple services, which had to be somehow taken apart, and now they are calling these multiple services, and this is also creating overhead. This needs to be redesigned so that they will be more efficient, and we are using a lot of sticky routing, which means that all the requests for one player get routed into one server in the cluster. So we are guaranteeing that all of the requests are routed into one server. And this enables us to use a lot of local caching, and we are executing these requests in all of the players have the separate queues, and we're executing these requests sequentially. So we don't have to worry about altering the player status simultaneously by two different threads. So it's so all them per player it is kind of like a single-threaded system, and then we can reduce the contention on locks and remove some of the locks that we had before. But now this sticky routing needs to be somehow implemented into this cloud system, or we have to somehow stop using this. And this is something that we have to figure out. And then there's moving the local caches into the shared caches. As I mentioned, we are relying a lot on the local caches in the system. And for example, this Nova has a service called the Rule Engine, which is processing our business rules, and it relies extensively on the local cache data. So we would need to move these local caches into a shared cache. We already are using Redis shared cache solution, but now we would have to move more and more data from the local caches into this shared cache, in order so that in the future we would have this possibility to move these services into a separate servers. And then there's the problem of bringing developers and product operations and deployment teams more together. Because initially, when Playtech started, it was a small startup. It was all done by one team, and eventually it grew, and the 3 separate teams were formed. And while at the beginning the people had the knowledge about the system because they all grew out from the same team, but as time passed on, the product operations guys would not have as much knowledge of what is going on in the development. In the development teams, and if you are introducing new servers, then it hits hard in the product operations, because they have to somehow support these. They have to debug the communication, which is now moving around between these new servers, and they have to somehow read these log files that these new servers have. So. As a conclusion, we think that the microservices approach may offer us a better tomorrow. It definitely comes with its own downsides and challenges, and it will increase our system's load or the load on the networks, and then we somehow will have to sell it to the management and tell them that we're building this system. It's still, from the business perspective, it behaves as it did before, but now it requires a lot of more CPUs, and the network network is more, and a lot more network bandwidth. But besides these challenges, we are still moving towards this direction, but we are not there yet, and we will not be within a few months or half a year still. So that is all. Thanks for listening. And if you have any questions, you can go ahead.
I have a question.
Yeah.
Can you switch to the slide where you have all the services? The first services.
One moment. You mean this one?
Yes. There are told that the services shouldn't call to each other.
Directly, yes. They will call through the API modules, so that we would have the interfaces in these APIs, and so the service only knows about this interface, which is in the API. It has only a dependency on this API module, and the implementation, which is behind of this API, it is Spring will handle it. It will find this implementation for this.
So one implementation can call to the other API dependency.
Yeah.
Because next slides describe how one service calls the other service, but it went just through API.
Yeah.
Okay. But how you have your own some kind of network layer implementation of how the calls are going from API.
Yes, we're using our own protocol, which is as I mentioned, it is called Galaxy, really fancy name. It's a binary-based protocol which relies on a persistent protocol, which relies on a handshake in the beginning of it, and it is quite efficient, and it was built about 6 years ago, so it's something we have, but we are. Yeah, so this is what we're using inside of our system, and then we have in this router, which is facing the outside world, we have converters, automated converters in there, which convert it into RESTful or SOAP APIs.
And in your cloud slide, there was some animal for RabbitMQ.
Oh yeah, this is.
Did you change to that instead of your own Galaxy? Or
This is something which we tried in the proof of concept. And what we tried was that this well, yeah, it's maybe not the best diagrams, but this existing router, it's just, at the moment it is dealing with this Galaxy requests, and so and the communication between Nova and existing routers is used by our proprietary protocol, but and now with this proof of concept, we would introduce this communication between this new service and the existing router with this RabbitMQ, so that we would plug it into this one router, so that there would be a conversion between this our existing protocol into the RabbitMQ, and the message would be sent to the service. It's still. Yes, it would be the future that we would start moving this. Actually, the next steps would be that we would start moving the Nova into the Cloud Foundry, and hopefully the other services as well. So that in this Cloud Foundry, the Cloud Foundry would manage the RabbitMQ as well, and then the RabbitMQ instances, and so it would all communication would be in there. So this is where we want to move, but this was just a proof of concept which we did to see if it's possible to get our existing servers working with this supposedly new solution where we would like to move. Because as I mentioned, we have 20 different servers, and it would not be viable to move all of them into this new solution at once. So we would probably have the ones who are creating the most network traffic in the side of either the Cloud Foundry or with our current solution. We would make a switch for them in one point, and then later on we have this few services which would have to use this this conversion solution until we move them as well. Yes.
Each of the servers potentially are like services that you microservices. They can move at different rates, grow at different rates. Have you thought about how version services with dependencies between them don't break?
There were actually, if I remember, Pivotal had some sort of solution for it, but we've not come to this yet, because our separation into microservices is still everything is still inside of one application, and even the Cloud Foundry is not 100% sure direction. There's a possibility of using OpenShift, which is a similar middleware platform, and yeah, so unfortunately this is a challenge for the future for us. Yeah.
So the question is, do you have any reports in the system? And if you do, how do you bring the data together from, like, let's say, account services and wallet services?
To generate these reports, right?
Yes.
We are at the moment it is using Oracle database, which is not a good solution, and we have a project in works at the moment where we try to separate it into another data store, so that we would have a solution using Tallinn, if I remember correctly, which would take the data from the Oracle database. It would place it into a secondary database, which would be used for generating reports. And the reports which have the real-time requirements would still have to use the Oracle database.
So the main question is, do you use services for
reporting? No, the reporting goes straight into the database. This is not through the APIs. But we presume that the reporting is not altering the data in the database in any way. Okay, actually, as I can see, we've 4 minutes over the time, so I will. If there's any more questions, if not, then thanks for listening. And,